So I'm really excited to talk to you today about some of the work that we've been doing over the past couple of months, looking at the benefits and the costs of meeting the reserve and system service requirements on the grid from zero carbon providers. So as opposed to fossil fuel plant, which provide a large proportion of those services today. We've been working with IWEA, and what I will do in the presentation here is talk you through some of the results that have been coming out of that study and some of the messages which we're seeing land from that. So I won't say too much about Baringa. I know a lot of you are familiar with us. We are with the #1 ranked consultancy in energy, according to the Financial Times. I'm contractually obliged to tell you that. And many of you will have read our 70 by 30 report, and in that we demonstrated that 70% renewables is achievable in Ireland by 2030 at net zero cost to end consumers. If onshore wind, for example, can be delivered for 60 euros per megawatt hour levelized cost. And any cost reduction below that level then delivers a financial benefit to end consumers. We also showed that all of the wind that's been deployed to date in Ireland, right from 2000 up to 2020, has been delivered at a net cost to end consumers of €1 per person per year. So really probably significantly lower in terms of the net cost than would be the popular kind of perception, I think, around the deployment of wind so far. And I think both of these studies have already gained a lot of traction around policymakers. And of course, we've seen the shift in government policy, and we now have the 70% target by 2030, and we have a clear aspiration and an evolving roadmap out to a net zero situation by 2050. What we found in that analysis is that the provision of flexibility on the power system was really key in efficiently integrating high levels of renewables over time. And that can take the form of battery storage, demand-side response, interconnection. What we wanted to do is to build on that finding and look at the potential benefit that could be derived if zero carbon sources of reserve and other system services were brought into play to replace some of the fossil fuel providers that we see today. And so we've analyzed those costs and benefits, and I'll take you through some of the approach to that in a second. I'll then take you through the results, and I'll draw a couple of emerging conclusions from what we're seeing. So we have used our in-house modeling capability to try and determine what the additional system costs are which are associated with meeting constraints and reserve right now on the system. And those costs at the moment are primarily being derived from the fuel, carbon, and other variable generation costs of fossil fuel assets. So this is really all about the repositioning of assets by EirGrid on the system such that they are in a position to provide the required amount of reserve and the required amount of other system services to the grid. So you have fossil fuel plant being turned on and quite often sitting there in a part-loaded state, running primarily to provide that headroom and reserve on the grid. The approach that we've taken is analogous. It's pretty close, I think, to the approach that EirGrid would take in its projections of the imperfections costs on the grid. I guess one important difference is that we are not looking at the line level of detail. So we are not modeling individual lines on the network. We're looking at overall system constraints. What that means is that the figures in terms of the savings and benefits that I'll show you today are very likely to be underestimates and are likely to be conservative versus the true benefits. So for the backdrop to this analysis, we used the 70 by 30 scenario that we'd already developed in that work. And I'll just take you very quickly through some of the key features of that. So we have about 10 gigawatts of wind on the island by 2030 in that scenario. We have just under 3 gigawatts of solar PV deployed by 2030. We increase the interconnection on the system, so we increased to around 2 gigawatts export capacity by 2025, and that's maintained through 2030. So we assume the addition of Greenlink, so another link to GB, and the addition of Celtic around 2025 as well, plus a little bit more export capacity on Moyle. We already assumed a significant quantity of battery storage in that scenario. So we had about 1.7 gigawatts of battery storage participating in the energy market by 2030 in that work. And in terms of the system constraints, so the main ones, the headlines, we were assuming that the SNSP limit would increase to around 90% by 2030, and that the min-gen constraint, so that minimum number of thermal units which needs to be running at any one time, would decrease from around 7 to 4 units over time. For the serious enthusiast, this is the full list of constraints that we're modeling and how they evolve over time. You'll be incredibly pleased to know I'm not proposing to go through this. The team back in the office will be mortified that I skipped over this, because it's incredibly important, but we'll move on past that. The first thing I just wanted to say before we go into the results is we're going to talk about these reserve providers. Some of those might be batteries. It could be things like demand-side response. What I wanted to just make the distinction around is that the 1.7 gigawatts of batteries that we already have in the 70 by 30 scenario are in addition to the reserve batteries that I'm going to talk about next. So we've got this 1.7 gigawatts, and we've done a number of calculations to determine that these are economically viable in that 70 by 30 scenario. So these are making their money from participating in the energy market, in the capacity market, and providing actions in the balancing market, and they are economic on that basis. And then the reserve batteries would be in addition to those. Okay, so I think let's have a look at some of the results. And what our analysis shows is there is an annual system cost saving of around 56 million euros per year by 2030 if all reserve is sourced from zero carbon sources. And you can see that saving ramps up over time. So in particular, we get a ramp up in 2025 up to 40 million euros a year, and then increases through to 2030. The majority of that saving is coming from avoiding having to pay the fuel and carbon costs for fossil fuel plants sitting there running at min stable in order to provide that reserve. What we then went on to look at is what the benefit would be if you not only met the reserve requirement from zero carbon providers, but you also met the other constraints on the grid from those providers as well. And this may require other technologies. This would not be possible purely with batteries or with demand-side response. You may need things like flywheels or StatComs or synchronous condensers or things like that. But the technology basically exists for this. And if you could do that, then you would unlock a saving for end consumers of around 114 million euros per year by 2030. Baked into this analysis is this assumption that the constraints on the grid are reduced over time. If that didn't happen, or if that was delayed, then that would actually increase this benefit. So there would be upside on this if there was any delay in reducing those grid constraints. we also then looked at what the benefit would be if just 50% of the reserve was met by by zero carbon providers. And the very interesting thing around this is that the initial results suggest that the benefit is only, in fact, only marginally lower than when 100% of reserve is sourced from zero carbon sources. So you can see here, comparing the light blue and the pink bars, by 2030, the two are actually very similar. But there are a few complex interactions underlying this result. And really what happens is that you have still the other constraints on the system and on the grid. And so removing the reserve constraint beyond that 50% point actually doesn't deliver any more benefit unless you address some of those other constraint requirements. In effect, the requirement for provision of inertia and for other system services is giving free reserve and free headroom, because you've got that anyway in the system because you're having to meet these other constraints. And I think this really underscored for us the importance of considering zero carbon providers of the full range of system services. So if you want to unlock the full benefit, looking at these other technologies as well alongside DSR and batteries is quite important. So just to wrap this up in terms of the economic message, what we're saying from the modeling we've done is that if zero carbon reserve can be delivered for less than around 120 to 160 euros per kilowatt, this will deliver a net financial benefit for end consumers. And what I've done is I've tracked that break-even point here for both the 50% reserve provision and the 100% reserve provision set of modeling that we've done. And just as an indication, I've plotted the approximate annuitized cost of battery storage reserve provision with this dotted line here. And you can see that already you can deliver battery storage for much less than the benefit which will be accrued over the mid-2020s and onwards. So, you know, that really there's no doubt that from the analysis we're seeing that this is viable and that the benefit is there. And alongside the financial benefit, you get actually a very significant CO2 emissions benefit from this as well. So you can deliver, in the case where you source all of your reserve and constraint requirements from zero carbon sources, you can cut 1 million tons of CO2 per year off power sector emissions. So current power sector emissions in Ireland are around the 11 million tons of CO2 per year mark, and we expect that to drop by around half by 2030. So this would be equivalent to taking out around 20% of total power sector emissions in 2030 under this kind of scenario. So it's a really material contribution to decarbonisation. There are also potential benefits linking with Rory's talk on wind curtailment as well, because if you can remove some of the requirement to have this underlying fossil fuel plant running on the system and taking up space that wind or renewables or solar would otherwise occupy, then you can really reduce curtailment levels. And so what we found is that you can halve wind curtailment levels and solar curtailment levels potentially in 2030 if you fully switch to zero carbon provision of system services. So a very, very substantial contribution in that regard as well. This analysis is relatively hot off the presses, and we're still trying to work through some of the detail of what this means. So what I've done here is just pull together some of my initial thoughts on what I think we can take from the analysis at this stage. So I think, first, meeting constraint and reserve requirements using fossil fuel plant is increasingly going to become a blocker to the decarbonisation of the system. It's going to end up with a requirement to retain this plant, which is only really needed on the system for that system service provision. Our analysis is showing that you can save around 55 million euros per year by 2030 by sourcing reserve only from zero carbon providers. And if zero carbon reserve can be delivered for less than around 120 to 160 euros a kilowatt, this will deliver net financial benefits for end consumers. And we know that relevant technologies can already be delivered at way lower cost than that. If other system constraints are also met from zero carbon providers, the benefits increase to around 114 million euros a year. And it certainly seems that this, from our analysis, is a clear win for end consumers. And it's also incredibly well aligned to both the government's climate action plan, the CRU's mission to try to work towards a more sustainable low carbon future, and EirGrid's strategy of reducing emissions from its own operations. I think then, just as a final point, our analysis has really focused on the fundamental cost savings which can come from this zero carbon reserve provision. I think alongside that, and something that we haven't been tasked with looking at, is the need to really consider what kind of market design framework is required to deliver this, and to deliver it in an investable way such that these assets can be brought forward viably by developers and investors. I will stop there, and I'm sure there'll be a chance for questions shortly. Thank you very much.